All right, welcome to the Explainer. Today, we're going to put on our detective hats. The case file we're opening up is this really dense but foundational physics paper from 1993 by John David Crawford. Now I know, the title is a total mouthful. Amplitude expansions for instabilities in populations of globally coupled oscillators, but what it's really about is solving this awesome mystery. How does order just pop out of chaos? We're going to unpack this thing piece by piece and figure out how millions of totally independent chaotic things, think flashing fireflies, neurons firing in your brain, even pacemaker cells in the heart, how they can all of a sudden start acting together in perfect synchronized harmony. This isn't just some abstract math puzzle, it's about the fundamental rules that run complex systems all around us. So, let's dive in.
Okay, so here's the game plan for how we're going to crack this case. First up, we'll set the scene with the oscillator mystery. You know, what's the core problem we're even trying to solve here? Then, we're going to see how physicists decode the population, which is a fancy way of saying they turn an impossibly messy problem into one clean, elegant equation. After that, we'll get to the good stuff, the tipping point. This is that critical moment where chaos just gives up and order takes over. From there, we'll explore the two different ways this can go down in synchronization versus oscillation. And then, the climax of our story, standing waves take over, where Crawford's analysis finds this crucial mistake in what everyone else thought was true and basically solves the case. And to wrap it all up, we'll piece together all the clues and build a map of behavior, a really powerful tool for predicting what these complex systems are going to do next.
You know, every great detective story kicks off with a really compelling puzzle. And ours is a phenomenon you can literally see in nature. Just picture a riverbank at dusk, and it's filled with thousands and thousands of fireflies. At first, they're just flashing randomly. It's a beautiful but completely chaotic, twinkling mess. But then, you start to notice something. Slowly, little patches of them start to blink together, in unison, until the entire swarm is pulsing with this one single collective rhythm. It's incredible. And the same thing happens with neurons in our brain, with pacemaker cells in our hearts, even with a bunch of pendulum clocks you hang on the same wall. They all just have this tendency to sync up. So the mystery is, why? Why does this happen? And maybe more importantly for us, can we actually write down a mathematical theory that predicts exactly when and how it's going to happen?
Okay, this quote right here, this is our central clue. This is the big idea that our entire investigation is built on. Crawford, and he's building on the work of some real pioneers like Winfrey and Kuramoto. He's basically telling us the secret to making this whole problem simpler. He's saying, look, instead of trying to track every single tiny detail of each firefly's flash or each neuron's firing cycle, things like its brightness, its chemical levels, its voltage, we can just ignore almost all of it. We only need to focus on one single crucial variable, its phase. And the phase is really just where is the oscillator in its own repetitive cycle. Think of it like the second hand on a clock. Is it at 12, at 3, at 6? By boiling down a super complex event to just a single number, its phase, we can create this self-contained or autonomous mathematical system that really gets to the heart of synchronization. This is our first huge breakthrough.
So this is our main tool. This is our magnifying glass for the whole investigation, the Kuramoto model. So let's break down what's going on inside this famous equation. On one side of the equation, you've got the rate of change of an oscillator's phase. Basically, how fast is its little clock hand turning? And on the other side, you've got the stuff that determines that speed. First, you have its own natural frequency, which the paper calls omega I. That's just how fast it wants to tick all by itself. Every firefly is a little bit different, right? So each one has its own unique omega I. But then comes the really crucial part, the interaction with all the others. This is controlled by something called the coupling strength, K. Think of K as how much peer pressure there is in the system. How much do these oscillators influence each other? And that coupling strength gets multiplied by the average influence from every other oscillator in the group. And how do we calculate that influence? Well, we use a simple sine function of the differences in their phases. Now, why a sine function? It's actually genius, because it perfectly captures this idea. When two oscillators are perfectly in phase, their phase difference is 0, and the sine of 0 is 0. So they don't push or pull on each other at all. But when they're the most out of phase, the sine function is at its maximum, and the pull to get in sync is the strongest. It's just this beautiful, elegant mathematical way of saying, the further you are from me, the harder I'm going to pull you back towards me. And that's it. That one beautiful equation models this incredibly complex social network of oscillators.
So we have our model. What are we actually trying to find? We are hunting for a phase transition, and the paper gives us a way to measure this. It's called an order parameter, and it's labeled R of t. This is a really clever mathematical trick. So imagine each oscillator is a little dot on a circle. R of t calculates the average position of all those dots. So if the oscillators are all over the place, flashing randomly, their average position is going to be right in the dead center of the circle. So R of t will be basically 0. That's what we call the incoherent state, total chaos. But if they start to bunch up, if they start to flash together, their average position is going to move away from the center, and R of t will suddenly become greater than 0. That's our signal. That's the flag that tells us a synchronized state of order has just emerged. So, our whole investigation now boils down to one thing: finding the exact conditions, specifically that critical coupling strength Kc, that make R of t spontaneously grow from 0. That is the mystery we have to solve.
Okay, so we've got a model for one oscillator talking to another. But in the real world, we might be dealing with millions or even billions of them. I mean, trying to solve that equation for every single one, that's just computationally impossible. So to move forward, our investigation needs a much more powerful approach. We need to stop looking at individual suspects and start looking at the behavior of the entire crowd. And this right here is where the real genius of the physics approach kicks in.
This slide shows the huge conceptual leap we're about to take. We start with our individuals, right? Each with its own phase. Then we make this really powerful assumption, which works great when n is huge. We're going to blur them all together. We treat them as if they were a continuous fluid, or a population density, which the paper calls rho. So instead of asking, hey, where is oscillator number 57, we now ask a totally different kind of question. What fraction of the entire population has a phase somewhere between 30 and 31 degrees? See the shift? This change in perspective is everything, because now we can bring in the big guns, the powerful tools of calculus and fluid dynamics. We get to trade millions of simple, interconnected equations, one for each firefly, for a single, much more complex but ultimately solvable master equation that describes the flow and evolution of this entire oscillator fluid.
And here it is. This is our master equation, the Fokker-Planck equation. I know it might look a little intimidating, but at its heart, it's really just a conservation law for our oscillator fluid. Let me break it down. The term on the left, delta P over delta T, that's just the rate of change of the density at a certain phase. How is the population at that spot on the circle changing over time? On the right, we have the two things that can cause it to change. The first bit is the drift term. This just describes how the density gets carried along with a velocity v. And this velocity v isn't just random. It's determined by the physics of our Kuramoto model. It's the oscillator's natural frequency plus that collective pull from the rest of the population. The second bit is the diffusion term. This describes how the population spreads out, kind of like a drop of ink in water, because of random noise, which we represent with the letter d. So the whole equation is just saying the change in population at a certain spot equals the net flow of oscillators moving into or out of that spot plus any spreading caused by noise. And just like that, this one equation now holds the dynamics of the entire system.
So, now that we have our master equation, the real forensic work can begin. We have a prime suspect for the system's default state, the incoherent state. Remember that? That's the state of total chaos, where all the oscillators are spread out completely evenly around the circle. Mathematically, this is just a uniform distribution. Rho 0 equals 1 over 2 pi. And it's an equilibrium of our Fokker-Planck equation. Why? Because in this state, the order parameter r is 0, so there's no collective force pulling things around. Everything is balanced. But is this state the one we're always going to see? Is it stable? That's our next step. We have to test its stability.
This really is the million-dollar question. I mean, if the chaotic, incoherent state is always stable, then synchronization would be totally impossible. Ordo could never just emerge on its own. So to answer this, we're going to perform a kind of forensic stress test. It's called a linear stability analysis. The idea is actually pretty simple. We take our system, which is sitting perfectly in its chaotic equilibrium, and we give it a tiny, tiny little kick, a small perturbation, and then we just watch and see what happens. Does the system just absorb that little shock and settle right back down into chaos? Or does that tiny kick trigger a massive chain reaction, growing and amplifying itself until the whole system is forced to abandon chaos and reorganize itself into a brand new state of order?
And this slide shows our primary forensic tool for figuring that out. To analyze what happens to that little kick, Crawford rewrites the master equation to focus only on the deviation away from the perfect chaotic state. This gives him a mathematical operator, he calls it L. And the behavior of this operator is completely determined by its eigenvalues, usually written as lambda. You can think of an eigenvalue as a number that tells you everything you need to know about how that little disturbance is going to evolve over time. It has two parts. The real part of the eigenvalue is the growth rate. If the real part is negative, any disturbance shrinks exponentially and just dies out. the chaotic state is stable. But, and this is the key, if we find even one single eigenvalue with a positive real part, that means there's a specific pattern of disturbance that will grow exponentially. It's unstable. The imaginary part, by the way, tells us the frequency, whether or not the disturbance oscillates as it grows or shrinks. So our job as detectives is to find the exact conditions where the real part of an eigenvalue crosses that line, from negative to positive. That's the tipping point we're looking for.
And that critical moment, that tipping point, has a name. It's called a bifurcation. This is where the story takes a sharp turn. Imagine we're slowly turning up a dial. That's our parameter, the coupling strength K. As we slowly increase K, the eigenvalues of the system are moving around. For low K, they're all safely in the negative zone. Everything is stable and chaos reigns supreme. But then, at a very specific critical value, K equals Kc, one of those eigenvalues crosses the imaginary axis, and its real part becomes positive. That is the bifurcation point. And at that exact moment, the system's behavior changes completely, qualitatively, dramatically. The incoherent state loses its stability. It's no longer a viable option. The system must transition to something new. The old world of chaos is gone. So the question now becomes, what new world does it find? And as we're about to see, there's more than one possible ending.
So, our system has hit its tipping point. The chaotic state is now officially unstable. It's got to go somewhere else. But what kind of order is going to emerge to take its place? Well, it turns out there isn't just one simple answer. The paper shows that, depending on the specific details of our oscillator population, two fundamentally different kinds of ordered states can be born from the ashes of that chaos. And this distinction is absolutely crucial. It's going to lead us right to the central finding of Crawford's entire paper.
Okay, so this slide perfectly contrasts the two possible fates for our system. And it all depends on how that critical eigenvalue crosses over into the unstable region. First possibility, if a single real eigenvalue crosses from negative to positive, we get what's called a steady state bifurcation. This gives birth to a new stable equilibrium. The order parameter R grows from 0 and then settles at a new steady non-zero value. This is that classic synchronization we were imagining with the fireflies. They all just lock into a fixed collective rhythm. Simple as that. But what if a pair of complex conjugate eigenvalues crosses the axis together? These are two eigenvalues that are basically mirror images of each other. Well, that's when we get a hop bifurcation. And a complex eigenvalue always means oscillation. So this kind of bifurcation doesn't create a new steady state, it creates a limit cycle. The order parameter R itself starts to oscillate in a regular, predictable pattern. This isn't just simple synchronization anymore. It's a much more complex, dynamic pattern. It's like waves of synchrony are pulsing and washing through the entire population.
And here we are. We've arrived at the climax of our detective story. We now know that the system can become unstable through something called a Hopf bifurcation, which leads to some kind of oscillating behavior. But what kind of oscillation exactly? Now, other people had looked at this exact problem before, and they had come to a conclusion. But Crawford, by looking much closer at a very subtle but incredibly powerful clue that others had missed, is about to completely overturn their verdict.
This right here is the crucial clue: O2 symmetry. You know, in physics, when you find a symmetry in your problem, it's like finding a key that unlocks a much deeper understanding of the whole system. A symmetry is just a transformation you can do that leaves the fundamental equations looking exactly the same. And it turns out the Cruel model, under certain conditions, has this beautiful O2 symmetry. It has two parts. The first is rotations. If you just shift every single oscillator's phase by the same amount, say 10 degrees, the overall dynamics don't change at all. That makes sense. The second part is reflections. This one's a little trickier. If the distribution of natural frequencies, that's our g of omega, is symmetric around 0, meaning you have just as many oscillators that want to go fast as you have that want to go slow, then you can flip the sign of all the frequencies, and again, the equations look exactly the same. Now, as we're about to find out, this symmetry isn't just some neat mathematical curiosity. It has profound, unavoidable consequences for what kinds of solutions can even exist.
So what's the consequence of this O2 symmetry? It's a really powerful constraint. In bifurcation theory, whenever you have a symmetry like this, it forces your eigenvalues to be degenerate. That just means that multiple distinct patterns of instability can all have the exact same growth rate. They become unstable at the exact same moment. Specifically, for this problem, the O2 symmetry forces the critical eigenvalue at the Hopf bifurcation to have what's called a multiplicity of 2. This means it's not just one unstable mode that starts to grow. There are two independent patterns that become unstable at the exact same time.
And Crawford points out that a previous analysis by Benilla, New, and Spigler had totally missed this crucial detail. They basically only included half of the unstable modes in their analysis. And as any good detective will tell you, if you ignore half the evidence, you are absolutely going to come to the wrong conclusion.
And boom! This table right here, this is the aha moment of the whole story. The previous work, because they only considered one unstable mode, predicted that the hop bifurcation would lead to something called a stable traveling wave. You can picture that as a single, coherent pulse of symphony that just moves continuously through the population, like the wave at a stadium. But Crawford's analysis, which correctly includes both of the unstable modes that are forced to exist by the symmetry, it reveals a completely different picture. These two modes can interact with each other, and the math shows that the traveling wave state is actually unstable. The other possible outcome, though, is something called a standing wave. This is where you have two waves of synchrony traveling in opposite directions, and they create this stationary, pulsating pattern of order, almost like the surface of a drum vibrating. And Crawford's more complete analysis shows that this is the stable outcome. The system doesn't choose the traveling wave, it chooses the standing wave.
So this is it. This is the final verdict. The case is officially solved. The prediction of stable traveling waves? It was an artifact, a ghost that was created by an incomplete calculation. By properly respecting the full O2 symmetry of the problem, Crawford corrects the scientific record. What he shows is that when a population of oscillators with a symmetric bimodal frequency distribution, that just means a population with two preferred frequencies, two distinct groups, when that system undergoes a hopped bifurcation, the state that actually emerges is not a single traveling pulse, but a stable, sloshing, standing wave. It's a much more complex and honestly a more beautiful form of order, and it's born from the interaction of these two distinct synchronized groups inside the population. So, with the central mystery now solved, we can finally step back and put all the pieces together. The analysis in Crawford's paper doesn't just solve this one specific case. What it really does is provide a comprehensive framework, a kind of map that allows us to predict what state the system is going to end up in just based on its initial conditions and its parameters.
This table gives us a really nice, simplified version of that map. It shows us how the final outcome depends on two key things, the coupling strength K and the shape of the frequency distribution G of omega. So, when the coupling K is below that critical threshold Kc, the incoherent state is stable. Chaos rules, no question. But when we crank up K above that threshold, what happens next depends on the population itself. If the frequency distribution G of omega is unimodal, which just means it has a single peak, like a classic bell curve, we get that steady state bifurcation which leads to a classic stable synchronized state. Simple. But if the distribution G of omega is bimodal, meaning it has two distinct peaks, representing two subpopulations that like to oscillate at different frequencies, well, that's the regime of the hop bifurcation. And as we've just spent all this time discovering, that leads to stable standing waves.
So let's just quickly recap the key clues from our investigation. We started with the Kuramoto model. That's the fundamental language we used to even talk about these systems. Then we made that huge leap to the Fokker-Planck equation to get a master view of the whole population at once. We learned that bifurcations are these critical tipping points where stability is lost and brand new states are born. And, maybe most importantly, we discovered that symmetry isn't just a minor detail, it's this incredibly powerful constraint that dictates what can and cannot happen. Respecting that O2 symmetry was the key that allowed Crawford to solve the whole case, proving that stable standing waves, not traveling waves, are the true signature of this kind of instability. And this really brings us to the ultimate significance of all this work. This isn't just about some abstract oscillators in a computer. The detailed mathematical journey we've just been on, from individual agents to a master equation, through stability analysis and bifurcation theory, it provides a universal blueprint. It's a powerful map for understanding and predicting the behavior of a huge range of complex adaptive systems, showing us how the simple local interactions of millions of individuals can give rise to these stunning, emergent, collective behaviors.
And that leaves us with this one final, really tantalizing question. The methods we've walked through in this paper give us this incredible lens to understand the transition from chaos to order. We've applied it here to a model of oscillators, sure, but the principles of symmetry and bifurcation theory are universal. They apply all over the place. So, what's next? Could we use this exact same framework to better understand the onset of epileptic seizures in the brain, or the flocking of birds, or even the crashing of financial markets, or the way public opinion forms? The map is in our hands now. The real question is, where are we going to explore next?
You know when you see a field of fireflies and they all start flashing in perfect unison? Or have you ever stopped to think about how the billions of neurons in your brain can suddenly fire together to create a single thought? Well, this spontaneous synchronization, it's one of nature's most incredible mysteries. And today, we're going to break down the beautiful mathematics scientists use to explain it.
I mean, this is really the core question, isn't it? You start with this massive group of individuals, every single one doing its own thing at its own pace, it's complete chaos, and then, almost like magic, they all fall into step. How does that even happen? It's this fundamental puzzle that shows up everywhere, in physics, in biology, even in how crowds behave. All right, so to really get to the bottom of this, we have to start thinking like a physicist, and that means we need to build a model. So first up, let's look at the basic building blocks they use to represent this amazing phenomenon.
So the key building block here is something called an oscillator. And honestly, it's just a fancy word for anything that has a natural repeating rhythm. A pendulum swinging back and forth, the beat of your heart, a firefly flashing, those are all oscillators. They're the individual members of that chaotic crowd that we're trying to figure out.
Okay, so you've got all these individual oscillators. How do you model the way they interact? Well, a scientist named Yoshiki Kuramoto came up with this idea that is just beautifully simple but unbelievably powerful. He basically said, what if each oscillator is a bit of a conformist? The rule is super simple. Each one slightly adjusts its own rhythm to be a little bit more like the average rhythm of the whole group. Yeah, it's pretty much a mathematical model of peer pressure.
So if we're talking about peer pressure, we need a way to measure it, right? We need a score. And for that, we use something called the order parameter, which we just call R. Think of it like a synchronization scorecard. If R is 0, it's a free-for-all, pure chaos. If R is 1, boom, every single oscillator is in perfect, unified sync. And of course, anything in between is some level of partial sync.
And that brings us to the starting line, for pretty much every system like this, what's called the incoherent state. This is the default. It's where there's no coordination whatsoever. The fireflies are all flashing randomly, the neurons are all firing at their own pace, and our sync scorecard, R, is sitting at a big fat 0. It's stable, it's predictable, and let's be honest, it's a little bit boring. But of course, the boring state isn't what we're here for. What we really want to know is how we get from that messy, chaotic state to something beautiful and orderly. And that transition, that's what happens at the tipping point. This is the million-dollar question. If chaos is the default setting, what has to happen to flip the switch? What's the trigger that pushes the whole system over the edge, causing that stable randomness to just shatter and give way to order? Well, physicists have a really clever way to find this exact moment. Picture this. Imagine trying to balance a pencil. When it's lying on its side on a table, that's our incoherent state. You can poke it, nudge it, it just settles back down. It's stable. But what happens when you try to balance it perfectly on its tip? The slightest breeze, the tiniest nudge, and it all comes crashing down. That's an unstable state. Scientists do the mathematical version of this. They start with a model in total chaos, give it a tiny little virtual nudge, and then they just watch. If the nudge fades away, the chaos is stable, but if that little nudge starts to grow and takes over the whole system, then the chaos was unstable. And that exact point where the behavior flips, that's the tipping point. Now, this critical moment, this tipping point, it have a technical name. It's called a bifurcation. It's this point where a tiny, smooth change, like maybe you're slowly turning up the strength of that peer pressure between our oscillators, causes this huge, dramatic, sudden shift in how the entire system behaves. The path forward literally splits or bifurcates from one state, chaos, into a totally new one, order. So, the system hits its tipping point. Chaos breaks down. But what fills the void? What does this new order that pops into existence actually look like? And what's wild is that the breakdown of chaos isn't chaotic at all. It's actually super structured. The math tells us that once that incoherent state becomes unstable, the system is essentially forced to choose between one of two main paths toward a new, orderly existence. And those two paths lead to really different places. On one side, you've got a steady state bifurcation. This one's pretty simple. Everybody just falls into one big synchronized group. All the fireflies flash at once. It's a static, stable, perfect harmony. But on the other side, you can get a hop bifurcation, and this one is way more dynamic. Instead of one big group, you get these oscillating patterns. So think of two separate groups of fireflies flashing back and forth, one after the other, in this perfect rhythm. It's a stable but constantly moving dance of synchronization. And this right here brings us to the core discovery of the paper that inspired this entire explainer. See, for years, there was this big debate about what happens after that more complex hot bifurcation. And the answer, as it turns out, was hiding in the model's symmetry.
Yeah, the scientific community was really kind of stuck on this. When these dynamic, wave-like patterns emerge, what do they eventually settle down into? Is there one specific pattern that's more stable than all the others? And different researchers, well, they were getting different answers from their models. So one of the big theories from researchers like Bonilla, New, and Spiegler predicted that the final stable outcome would be something called traveling waves. The best way to picture this is the wave at a sports stadium. It's a pulse of synchronization that actually moves through the population. But this is where J.D. Crawford, in the paper we're focused on, spotted a flaw in that logic. He realized that those earlier models, they were incomplete. They had correctly found one way the system could behave, but they had missed other possibilities because their analysis just wasn't deep enough. They hadn't accounted for everything. And the missing piece was this really deep property in the math called O2 symmetry. Now, without getting too bogged down in the equations, what this basically means is that the model works exactly the same if you rotate all the oscillators together or if you reflect them, which is like running their cycles backward. This hidden symmetry forces the system to behave in very specific ways, and the earlier models just hadn't fully wrestled with all its consequences. This table lays out the whole scientific detective story perfectly. You had Bonilla and his colleagues predicting traveling waves because their analysis was missing a key piece of that symmetry puzzle. Then, at about the same time, you had Okuda and Kuramoto, who actually predicted the right answer, standing waves, but they didn't have the hardcore mathematical proof to show why they were right. And then comes Crawford, who puts it all together, using a rigorous, complete analysis of that hidden O2 symmetry to prove once and for all what really happens. And so the final verdict was in. When you properly account for the model's full symmetry, the math is crystal clear. The stable, long-term pattern isn't a single traveling wave. It's standing waves, those two groups pulsing back and forth in that stable, rhythmic dance. It was just a powerful reminder that in physics, getting those fundamental principles like symmetry exactly right, well, it's everything. Okay, so that's a fascinating piece of mathematical detective work. But why is this abstract debate from decades ago so important? Well, because it was never just about fireflies. The rules that govern these oscillators, they apply to countless systems in our world. I mean, just think about it. Your brain is a network of oscillators. An epileptic seizure is, in a very real way, a bifurcation event, a sudden, catastrophic, and unwanted synchronization of neurons. A nation's power grid is a network of generators that all have to stay perfectly in sync to prevent blackouts. You can even model the spread of a disease as oscillators tipping into a synchronized, infected state. Understanding these tipping points from chaos to order is absolutely fundamental to managing the world around us. And that leaves us with this one last kind of mind-bending thought to chew on. We usually think of the complex, beautiful patterns we see in nature, the stripes on a tiger, the spiral of a galaxy, as products of chance and evolution. But what if they're not? What if, just like the standing waves of our fireflies, they are the direct, inevitable results of deep, hidden mathematical symmetries that are woven into the very fabric of our universe? It suggests that underneath all the chaos, there's a profound and elegant order just waiting for the right moment to emerge.
You know that moment when you see a massive flock of birds turn in perfect unison, or a whole field of fireflies starts flashing all at once? It feels like magic, right? Where all this chaos just suddenly snaps into perfect, beautiful order. But what if I told you it's not magic, it's math? Okay, let's get into this.
I mean, this is one of the most fascinating questions out there. And you see it everywhere, not just in nature. Think about neurons firing together in the brain, or even a huge stadium crowd totally disorganized 1 second, and then they all start clapping in perfect unison. You have a group of individuals, each with their own rhythm, and then bam, they're all acting as one. So how does that happen? And maybe more importantly, can we predict the exact moment it's going to happen?
Well, the answer is a big, resounding yes. And the key is this incredibly powerful mathematical toolkit that lets physicists dig into these super complex systems. Today, we're going to be looking at a classic paper by John David Crawford that lays out this very toolkit. So get ready, because we're basically going on a scientific detective story to find that precise tipping point between total disorder and perfect mass synchronization.
All right, so to kick off our investigation, we need a suspect, right? We need a model of the system that we can actually analyze. And what physicists usually do is start with a simplified but really powerful set of rules that describes how our crowd behaves.
So this is where it all begins, the Kuromoto model. Just imagine every firefly, or every neuron, or every pendulum as an oscillator. Each one has its own natural rhythm, its own frequency. Now, the really crucial part is that they are weakly coupled. That just means they can influence each other, but only a tiny little bit. And you gotta know, this isn't just some toy model for fun. This thing is a workhorse in science. It's used to study everything from how our brain cells coordinate to how entire power grids stay stable. It's a big deal.
And this is where it gets really interesting, because this shows the two possible outcomes for our crowd. Over on the left, you've got the incoherent state. Basically, everyone's just doing their own thing. The overall order, which we measure with this value we call R, is pretty much 0. But then on the right, you have the synchronized state. Everyone is acting together, and that R value is high. The central mystery, the whole point of this, is what causes that jump from the left side to the right.
So how do you even begin to tackle this? I mean, tracking millions and millions of individual oscillators is, well, it's just impossible. So physicists make this brilliant conceptual leap. Instead of trying to watch every single individual, they figure out a way to describe the behavior of the entire crowd all at once.
And this right here is the great simplification. This is the genius move. Just forget about tracking firefly number 1, firefly number 2, number 3, and so on. Instead, like you see in step 2, we create a single, elegant mathematical function that just tells us the density of oscillators at any given phase. It's kind of like looking at a satellite map of traffic instead of trying to track every single car on the highway. This move right here is what makes the whole problem solvable. It's everything.
And what you're seeing here, this is the result of that simplification. We now have one single powerful equation, the Fokker-Planck equation, to govern the evolution of the entire population's density over time. It's basically a master equation. It tracks the probability of where you'll find an oscillator at any given moment. With this one tool, we can predict the behavior of millions. It's our master key to unlocking this whole mystery.
Okay, so now we have our mathematical model of the crowd. We've got our suspect, so to speak. Now we can start, well, poking at it. The goal here is to perform what's called a stability test, to figure out exactly when that disordered, incoherent state is about to just collapse and give way to order.
To do this, we calculate this special number called an eigenvalue, which we represent with the Greek letter lambda. Now, don't let the name scare you. You can just think of lambda as the system's stability score. Let me give you an analogy. Imagine a ball on a hilly landscape. If the ball is resting safely in a valley, that's like having a negative eigenvalue. If you give it a little nudge, it just wobbles and settles right back down. But what if that ball is perched on the very, very peak of a hill? Well, that's like a positive eigenvalue. The tiniest, slightest push will send it rolling away and everything changes.
And this table here, it just lays it all out perfectly. If our stability score, lambda, is negative, the system is stable and it's disordered state. It's the ball in the valley. Any little push just dies out. But if lambda is positive, the system is unstable. That tiny nudge grows and grows exponentially, and boom, synchronization happens. The entire investigation, the whole search, it all comes down to finding the exact moment that lambda crosses from negative to positive. That single point, that's our tipping point. That's what we're looking for.
All right, so the big question is, what actually happens when that score does cross 0, when the system finally becomes unstable? Well, it turns out there isn't just one way for order to emerge. Let's take a look at the first, and maybe the most straightforward possibility.
So one way this can happen is through what's called a steady-state bifurcation. Bifurcation is just a fancy word that means a splitting or a forking in two. The system hits a point where its old behavior is no longer stable, so it has to choose a new path. In this case, the system basically just flips a switch. It goes from that incoherent state to a new, stable, synchronized state that doesn't change over time. You can imagine all the fireflies flashing randomly, and then suddenly they all just freeze in a unified lit-up pattern.
So, you might be thinking, okay, the system just flips a switch to a new, frozen state. Simple, clean outcome. But that is not the whole story, and this right here is where Crawford's paper reveals this really surprising and, honestly, beautiful twist in our detective story. It turns out the transition to order isn't always a simple switch. Sometimes it's something way more dynamic. And here you can see the two paths side by side. On the left, you've got that simple switch we talked about, but on the right, we have something much more spectacular, a hop bifurcation. In this case, the system doesn't settle into some static pattern. No,
Instead, it erupts into a dynamic, rhythmic pattern. These waves of synchrony that actually pulse through the population. You know, it's the difference between a light switch just turning on versus a speaker suddenly emitting a perfect pulsing, living tone.
And this right here, this is the absolute crucial insight from the paper. See, previous work had predicted different outcomes, but Crawford's super rigorous analysis, which correctly included all the ways the system could become unstable, showed something totally new. He proved that in this model, the stable outcome wasn't traveling waves, but these beautiful, pulsing, standing waves. He literally corrected the scientific record, showing us the true nature of this emerging order.
So, okay, we've solved the mystery for our population of oscillators. We've cracked the case. But the real power of this story, the real reason we're talking about it, isn't just about fireflies or pendulums. It's about the universal nature of the tools we use to get here.
What we've been using is a mathematical framework known as bifurcation theory. At its heart, it's really the study of tipping points, those moments when a small, smooth change in a system causes a sudden, dramatic shift in its behavior. It gives us a precise language to describe these moments, it uses deep ideas like symmetry to cut right through the complexity, and it lets us derive simple equations that predict exactly what kind of new order is going to emerge. It's an incredible toolkit.
And this is why this all truly matters. This isn't just some abstract math problem. This exact same toolkit is used to analyze real-world tipping points that affect all of us. Neuroscientists use it to understand how something like an epileptic seizure can suddenly synchronize huge regions of the brain. Engineers use it to predict when a power grid might become unstable and just collapse. And yes, climatologists use it to model how our planet's climate system might abruptly shift. It's the same math. These are the tools scientists use to predict and hopefully prevent these sudden dramatic changes in the world all around us.
So yeah, the next time you see one of those incredible moments of mass synchronization, remember the elegant math that's hiding just beneath the surface. And it just leaves us with this one last, kind of mind-blowing question. What other incredibly complex systems, from financial markets to social movements, have these hidden tipping points that are just waiting for the right mathematical toolkit to finally be revealed?